Yeah. Good. Okay. So today we're going to talk about graphical models, which is a favorite topic of mine because it involves drawing, or it can involve drawing, which is fun. Twitter and GitHub. I don't know why I put this on there. So let's just dive right in. I apologize for not being here the first 2 days. I had a different conflict, but from what I hear, you learned a lot about probability, and you started implementing some models using PyMC. The way I think of what probabilistic graphical models are a really useful visual way of debugging probabilistic models. So probabilistic model is a nebulous idea or thing that you can think of either as a bunch of probability distribution or in terms of this graph structure. The reason the word graphical or graph is in the name is because it uses concepts from graph theory. So that's a mathematical subfield that I know nothing about. But there's a couple basic concepts that we're going to go through that are important foundational things to know in order to start thinking about these things. Oh, one other thing I wanted to say is these slides are in the GitHub repository. So if you pull, in fact, everyone maybe should do a poll right now, because there's also a notebook that we're going to switch to in a little bit. But the slides are in there as PDF. So if you'd rather follow along on your screen, you can. Cool. So we're going to go through a couple fundamentals of graph theory as it relates to PGMs or probabilistic graphical models, and then start drawing models on the whiteboard or in TriPython notebook. How do I get rid of this? Go on hide video, including meeting controls. There we go. Okay. Good. So as I mentioned, so PGMs, I'm going to abbreviate it. It's a very long name, probabilistic graphical models. PGMs, sometimes we'll say graphical models. I personally find them most useful for sort of debugging the structure of a probabilistic model. And when I'm initially thinking about a problem, some parameters I want to infer in a functional model that I have, I usually start actually in my notebook by drawing out one of these graphical models. Then I go from there to thinking about, okay, what probability distributions are in the model. You can also go the other way. Maybe you want to start by writing down the distributions and then map out a graphical model, and that might help you find bugs in the way that you're thinking about the way that your parameters are related. They're also useful because, as we'll see, it makes it clear how to extend a model, how to build in other dependencies on parameters that you might have in a model. And I'm talking very abstractly now, but we're going to go into some very, very specific examples in a little bit. And so I just finally, as I already said, I find them, it is a whole field, and there's a lot of other things you can do with these in the math and statistics land. But in terms of astronomy and astrophysics, data analysis, I find them mostly useful for visualizing and sort of mapping out the relationships that you have between random variables in a model, or parameters in data. Okay, so this I hope is my only slide on graph theory, because like I said, I literally know nothing about graph theory. This is everything I know about it. It is a whole field, and there's lots of interesting things you can do with it. But these are the core concepts. So a graph, in our context, this is what you should visualize when I say the word graph, not like a chart with an x-axis and y-axis. A graph is a sort of network, another way of thinking of it. It's a mathematical structure for expressing relationships between objects that together might form some kind of network. And this thing down here, which is the graph, is made of two main types of things. One thing are the vertices. So a vertex or a node are these things, the open circles in my visual here. Those are the objects that you want to be able to visualize in some kind of network. The other type of thing that makes up this graph are the edges. These are the connections between the objects. And as we'll see in a minute, these edges can either be directed or undirected. So they can either be a line where there's symmetry between the two objects, or they can have a directionality to them. So maybe this object depends on this object. So not going to talk a lot about undirected graphs because I think in probabilistic context, we're going to mostly think about directed graphs. But just to flash one example up, there are other model contexts in machine learning and other places where you might see undirected graphs. These are networks where there's no inherent sense of direction or hierarchy between the different objects. So this is just a great example from New York City of a part of a subway line. So a subway map would be an undirected graph. You can move between the stations by taking the train or by transferring to another train line that's at the same station, but you can go either direction. There's no inherent asymmetry between the relationships between the stations here. By the way, I should have also said, interrupt me at any point. I'm happy to go off on tangents and questions. So again, I mentioned that's context. We're not going to talk a lot about undirected graphs. All the examples and the problems that we're going to do are going to be directed graphs because they're going to be probabilistic models. But an example of a directed graph that's not a probabilistic model is a family tree. So that's a case where there's some inherent asymmetry between children and parents, or people, generational relationships in a family. So you can have edges that represent this asymmetry going down. Now, there's one last word to get, and then we're done with graph theory, and we're going to talk about probability, probabilistic models. And that's the word that got shoved in the middle of directed graph, acyclic. And that's an important word here because in at least in the model building context that we're going to talk about, and basically every probabilistic model that I've used in practice, they are acyclic, which means that there's no closed loops. So notice that here, A points to C, C points to D, and D points to A again. That makes a cycle in this graph. And when you think about probabilistic random variables, we can't have these kinds of cycles in the types of models that we're going to be talking about. So the PGMs that we're going to focus on are inherently directed acyclic graphs, DAGs. Lots of acronyms. Any questions on that so far? Yeah.
Why closed cycle not allowed many sequence?
You mean not all?
Yeah.
So yeah, there are some kinds of like neural network type models where you can actually have cycles, but we're not going to talk about machine learning models. We're going to talk about random variable relationships. Yeah, and I should have had an example ready, but I can't come up with one off the top of my head. Okay, so in PGMs as DAGs, in the context of the probabilistic models that we're going to be talking about, the vertices in the graphs, or the nodes, if you want to think of it, those are equivalent words. They represent either parameters in your model or data. They can only be those two things. The edges that we're going to draw between the vertices represent the relationships or the dependencies that a variable or a piece of data has on other variables and other parameters in your model. And I think, so this sentence took me a long time to internalize and figure out. So I'm going to say it, but if it doesn't mean anything to you, that's fine. We're going to come back to it. I think the most important concept about probabilistic graphical models, the reason they're so useful, is that when you write down a graph representation of your probabilistic model, the core idea is that gives you a map of the ways that you can factorize the joint probability over everything that's in the model. Again, you might be like, whatever, but that turns out to be a really powerful thing, and we're going to come back to that many times. Yes?
Find the relationship between the parameters, what they do.
Yeah.
I mean, like, correlated or not correlated. Kind of stuff?
Good. Sort of. I'm being a little vague, and we'll see examples in a second. But what I really mean is that I think probably a lot of the models, the probabilistic models that we're going to be looking at, by the way, a brief tangent. The word model incredibly overloaded in all of this. So I'm always going to try to say a word before model, but that makes everything I say very long. Probabilistic model, graphical model, etc. Functional model. Those are all different things, but they all use the word model. But what I mean by relationship is that you might have a probabilistic model where a parameter in your model is related to another parameter through a functional model, meaning you might have a straight, like a y is data, you did the straight line example, you might have y is data, depends on two parameters, the slope and the intercept. That's a relationship. Those two parameters generate the data y, and we're going to see that. Good, so internalize that. When you have a graphical model, that gives you a map of how to factorize the joint probability distribution over everything that's in the model. Good. So we're going to start with an example, maybe two examples that I remember, and then we're going to do some breakout problems where we're all going to get up and draw graphical models together. Well, you all will together. So I want to start with an example that is relevant, that I do all the time, relevant in the Gaia era. And that the problem is we want to measure the distance or infer the distance to a star or a thing, and we have a measurement of its parallax. So in that case, the parallax is 1 over the distance. So that's a relationship, that's a functional dependence of some piece of data to some parameter in our model. Here you can think of the distance as a parameter in a model that we could write down. And if we wanted to write a graphical model for this probabilistic model, then it would be this. So parameter R points to piece of data parallax. So there's two conventions here that I want to introduce. One is, notice that this is shaded and this one is open, unfilled. This is a convention that you'll see a lot. Shaded nodes or vertices are pieces of data, things that you have observed, things that you have values for, and might be stochastically related to something else. Random variables or things that are unobserved or latent variables, those are all different names. Those are left unfilled, like this are. So what do I mean by a stochastic relationship? What I mean is, yes, you can write down an expression, parallax equals 1 over r, but by putting it in a probabilistic context, we would write down a likelihood, because this parallax probably has some noise measurement associated with it. So we would say that the parallax is related to this true parameter 1 over r with maybe Gaussian noise. So there's a distribution, a Gaussian distribution that is implicit in this connection here. Pausing for a second. How does everyone feel about that so far? I think this is the simplest model I could think of, and we're going to build up from there. Good. So key concepts here. Unfilled is unobserved. Filled is observed data. And the edge here, pointing from one to the other, the way I like to think of it is that's the direction that you would use to generate the thing that you observe. So in order to produce the observed parallax, I have to start with. I said all of that. So that's just reinforcing what I just said. So now, before I said, I'm going to say this many, many times just to try to get it into you. Earlier I said that a graphical model tells us the way we can factorize the joint probability distribution over all the things in the model. So what are all of the things that are in this model? Distance and parallax, just two things. So the joint probability distribution for everything in our model is P of R, comma, parallax. I think this is called bar pi in terms of the character, but anyway. This is the joint probability distribution over everything in our model. The graphical model tells us that the parallax depends on the value of the distance, but notice nothing points at the distance. There's no arrows pointing in at R. So that means that from looking at this graph, we can factorize this joint probability distribution into P of parallax conditional on R. So that's another way of thinking of this relationship, this arrow, is that it puts a conditional bar in your probability distribution. And then multiply that by P of R, and that gets no conditional because nothing is pointing at it. So in the context of what you've talked about already, this would be like a likelihood, because this is P of data given a parameter in the model, and then what would this be?
Right.
Good. Cool. So that's a totally valid probabilistic graphical model, and we could stop there. If we were working with this, we could just write that down and that would be fine. But there's one other convention that you might see that I want to introduce, because it is sometimes useful. Now, as someone just called out, I didn't actually see who said that. P of R is the prior PDF, another abbreviation, probability distribution function. I'm going to use that a lot because that's another big chunk of words. This prior might have its own parameters, but those, if we're using it as a prior, we have to fix all of those parameters. So they'll all have like numerical values that we drop in. So for example, maybe we have a prior that looks like this, and it has a parameter L, but we set L to 1. Sometimes you'll see people represent that kind of relationship using a node as a closed circle, small marker instead of a big open marker. And this means that it's kind of telling you that there is the prior, the distribution over R has a parameter, but we're fixing that parameter. So they're kind of useful for housekeeping, for remembering what distributions or variables or parameters go into priors, even if we fix them ahead of time. So the three concepts now, we have our unobserved or latent is unfilled, observed or data is shaded, fixed is a closed small marker. Now, those are sort of three core concepts in graphical models, and we're going to use those for some examples or for some problems in a moment. I just wanted to call back to something you may have seen, I think, in DJ's lectures or maybe in the tutorial, which is that a lot of the graphical models that I've drawn as examples here, I used this Python package called DAF, which is nice. It lets you construct these sort of pretty graph relationships. But the PyMC will actually automatically generate the graphical model for you. It's just a little bit uglier, so I don't like to do as much. So this is a model constructed for the distance parallax relationship that I showed you before. And if you do model to graph is, you end up with this. And the one thing that I will give it this is a little bit nicer because it tells you the distribution inside, whereas typically when you see a graphical model, it doesn't say what distribution each random variable is drawn from. Questions? Okay, we're going to dive right in with a problem. So in the IPython notebook, by the way, there's a ton of text in the notebook, which that you can skip. A lot of it is just generating the stuff in the slides or explaining what I already explained in the slides. But if you scroll all the way down to problem 1, that's what we're going to do now. So this is going to be similar to the distance parallax model, but with a couple other components to it. The setup is we have the parallax and the total proper motion, the magnitude of the proper motion vector u. So that's a scalar. And that's related to the tangential velocity of a star over its distance. So the task is to draw a graphical model for a probabilistic model in which we want to infer the tangential velocity and the distance, and we've observed the parallax and the total proper motion. So what I would say is pair up with whoever you're next to. And I think there's a lot of us, so we won't all fit on the board. But I think if we cut the boards in half, we might be able to do it. But the idea is we're going to go up to the board and try to map this out together. The other option is you can actually code it up using Daft if you really want to, if there's some examples above. But I think it's better to start with actually drawing this out. Cool. So yeah, let's cut all the boards in half. Not literally. Go. Yeah. Oh yeah. I see some excellent artwork on the walls, and I guess some of you worked on your iPads or notebooks. That's also totally fine. So this is closest to me and looks good. So I'm picking on Marcus. Would you mind replicating that right here, and so we can talk about it?
You mean like code it up, you think?
No, just write it on the board here.
Oh, I see.
Just because it's kind of hard to see over here.
So you have your observable, your observable parallax depends on R. U depends on two parameters, V tiny and quad.
Cool. That looks great to me. A lot of the models I see look like that. I like how someone has just gone chaos and not drawn top down. That's totally fine too. There's no rule that you have to go from top to bottom. This one is right, but it's inverted. So I wanted to talk about this one for a sec. Because this came up a second ago when we were chatting with someone else. Chatting with Abby. Sorry, I'm looking at your name tag. So one of the weird things about these relationships and these models that we draw is the thing you actually want to know are these things. And you might think we start with the data, so why don't the arrows point the other way? Like you give me the data and I want to go back to the parameters that we don't observe. And that's just, the whole challenge with writing down graphical models and probabilistic models is that you have to think in the inverse. You have to think in terms of the generation process, how the parameters, the things that we don't know, generate the data that we observe. So there's a generational thing also in physics. If you talk to some stuffy old physicists, they call this an inverse problem. You may have heard that terminology before. And it's precisely because of this structure. You observe these things, and you want to go the inverse direction to learn the things that generated the things that you observe. So you have basically the right relationship. You just have to flip all the arrows. I think everything else looks okay from what I can see. Did anyone have any questions about this? Otherwise, great work, everyone. Yeah.
Feeding in like L and like the upper motions are exact. We just like put those in like.
So for L, yeah, you would just put, someone even did this, I think. Oh yeah, it's back there. So that would be like that. And then, so proper motion and RA and DEC components, that would be a different kind of model because those would be observed things. And then you'd have to make it vector, and that would be fine.
Right.
So we could actually just do this. But yes, you might also have a prior on these. I mean, if we're turning this into a posterior probability distribution, you have to have a prior on that, and that might have parameters, and you would just draw it like that, kind of like the one in the back there. Yeah. So great work, everyone. I think everyone basically nailed it. So good job. And we're going to go from that right into another problem. So, oh boy. Same prompt. We're going to draw a graphical model. So you can just go back to exactly where you were, or if you drew on paper or your iPad before and you want to do it on the board, maybe take over someone's spot. But the idea here is it's same idea with same tools that we have, but we're going to do a different scientific context just to try to get you thinking about drawing these types of models. And of course, we all probably have a diverse range of interests in scientific research topics. So I want to try to bring in examples from different places. So this one is, we're going to try to infer the distance to a Cepheid variable star using a period luminosity relationship. So here, I'll go to the notebook in a second, but just to remind you, the mean flux is related to the mean luminosity over 4 pi distance squared. I used the funny L because I realized that we were using L for the distance prior in the previous example, so there's nothing special about this, it's just fancy. So here, the idea is the luminosity. The luminosity, which is unobserved, is related to the period, which is observed, through this linear relationship. So there's 3 unobserved things in here and 1 observed thing. But we also know the mean flux. That's an observed thing. And that's related to 2 unobserved things, the luminosity and the distance. So let's assume we observe the period and the mean flux and the parallax. And we want to infer the luminosity and therefore the distance. Same idea. Yeah.
So when you say where A and B are known values, that means can we attribute it to observed?
These are fixed values. So these are just like exactly fixed values dots. Yeah. So maybe some other survey did some calibration to determine the period luminosity relation, and now we're just treating those as fixed parameters from this other data.
Do we have to add parallax?
Did you want to?
Oh, actually, I don't think we need parallax. I said the word parallax, but we don't need parallax. Yeah. Yeah. Forget I said the word parallax. No parallax there. No parallax for you. Break before we dive back into some other things. Good. Okay. So these are all of the variables, parameters, or pieces of data that I mentioned. Would anyone like to come up and draw a relationship? Maybe Sabina?
Yeah.
Okay. And it matches your jacket.
Everyone points that out thing. Yeah, so the beta is P.
Excellent.
Oh, thank you. And flux.
I like your squiggle shade. Oh, by the way, there's a convention that you sometimes see also is sometimes people will do a double circle around things that are observed, just so you know, like occasionally that'll pop up in a paper. So sometimes that's useful for drawing on the board when you don't want to like shade in that thing. Sorry to interrupt you.
So we know the relationship between L and P, and L is something we want to infer. So we can go ahead and do what's there. And there's also a relationship between L and S. So it goes like this. R is another variable that we want to refer, another parameter, and it depends on, well, it depends on R. And we have to know values of A and B. That's actually what I was waiting. But they both, like L depends on A and B. And visually, like, I think it's better to write it like this. Yeah.
Anyone have thoughts about that?
Why would they be going to L when they?
Yeah, that's what I was debating as well. Because, like, I mean, sure, we can like rewrite P as being like as a function of P of like L.
Exactly. Yeah, that's exactly how I would think of it. In that case, we need to actually invert that mathematical expression because, again, we're thinking about generating the data that we serve, and the data we serve is P. So what things go into generating value of P, you rearrange that expression.
That's
good.
But I was also thinking about like visually, we want to know like the actual relationship, not like the inverse relationship, not things like that.
Yeah. No, that's a totally a good thought. Oh. Okay.
Why would you include A and B if you're not going to include 4 and pi as well?
That's a good question.
Yeah.
The distinction is that, well, A, it's K. Oh, yeah. Thank you. Why would we include A and B as fixed points in the model and not 4 and pi? You can. There's no rules. But really it's because A and B are, you want to like emphasize, it's kind of telling yourself that A and B are parameters or things that we're just fixing. They're parameters in an expression that we're going to fix the numerical values of. Yeah, one of the problems with graphical models is they don't actually tell you how to write down the model fully because there are factors like 4 and pi and 2, square root of 2, things like that aren't in the model. But that's okay. That we typically don't include them. Good. That looks good to me. So the A and B would point to P in this case. Because
P is dependent on A and B, B of A of B.
P, in order to get P, so what we wrote L equals A P plus B. And in this case, these are not random variables, they're just fixed numbers. So actually, we would rewrite this as L minus P over A equals P. And so in order to generate the value of P, we need the random variable of L and the 2 fixed values A and B. Again, you don't have, these are optional. The fixed ones are optional, they're kind of notes to self.
Suppose we have to change which one is of those value and we have to re-edit.
In this case, that's not always what you do. If A and B were random variables, it would actually be slightly different, but yeah.
So it's because you can put it's because it's a random variable
That's probably loud, sorry.
that it's not affecting A and B would not go into L because you're like choosing something.
Exactly, yes, yep, they're fixed values.
I mean, L.
L is a random variable, yeah.
Can I just check my understanding with you?
Please.
So in terms of posteriors and likelihood, F and C are like posteriors.
These are just so the question is, are F and P posteriors? I'm going to repeat for the microphone. In this case, these are all just variables or parameters for data. None of these are the distribution. Posterior means distribution, right? Yeah.
You do eventually want to think of it that way, don't you?
Yeah, sure.
So if you're going to do that, would P and F be posterior, and they would be likelihoods that,
Can I?
or no?
So,
L and R would be posterior?
so
The
none,
90 would be,
actually, Sabina, do you want to?
Yeah, yeah, I'm guessing that like our likelihood in this case would be like probability P given L plus like probability
Yeah.
plus the probability of F given L and F given R. Right.
Good. So we're gonna, after our break, we're gonna start writing down some joint probability distributions and start factorizing them. But let me give you a preview right before we take the break. So here, these are fixed values, so those don't go into a probability distribution. They're just numbers of 4 and 5. But all the other things are either random variables or observed things like data. So those could go into a probability distribution. So this is where I should have used a different letter for periods, but anyway, P of P, F, L, R. So this is the joint probability distribution over everything. So now let's try to factorize it and try to relate it to things like posterior likelihood prior. So let's start with the data. By the way, did anyone notice the trick that I played on you between these two graphical models? They're the same. Anyway, if you flip that one upside down, you'll notice that you have 2 unobserved things. They point to one observed thing, but there's one unobserved thing that points to 2. So anyway, this is just to point out that as you start writing down these graphical models, you'll start to notice sort of common structures that tend to appear, and this is the common structure. Yeah.
One thing I noticed about these graphical models is there's no information about power law dependence. Like, for example, parallaxes goes like r to the -1, so it goes like r to the -2.
Good. Yes. There's no information in a graphical model about the functional relationship or the stochastic relationship between the things. That's right. That's why I was saying the one good thing about the PyMC model is that it tells you the distribution on there, but that still doesn't tell you the functional dependencies. So it doesn't tell you parallax equals 1 over r. Anyway, let's just quickly do this and then break. So this is the joint probability distribution over everything. So if we look at P, we want to write down some distribution. Yeah, you can, sorry, P of period. So we start like this. What goes after the conditional for period?
Given L.
L. Good. Yes. Right, and so just to reinforce, the way you read this is P given L. You were all saying that already. Just want to say it again. So that's how you can factor out the conditional probability distribution of period. How about the other observed thing?
Given L and R.
R, L. And then what's left?
Good try.
So now that we've factorized this joint probability distribution, we can start to see things that are somewhat familiar to us, maybe related to the things that Ashad was saying. This is what I would call the likelihood, because it's P data given model parameters. And these are prior probability distributions. What's the posterior? So you remember that the posterior isn't exactly the joint probability distribution. Good, yeah. So if you just have, maybe you saw this, theta and d, this you can factorize to P of B given theta, P of theta, and the opposite factorization, P of theta given D, P of D, and this is the posterior. This is the joint, factorized joint probability. This is the posterior. So So the posterior is the joint over this thing. So in our case, this is the factorized joint probability. You would just have to divide it by a weird thing. You would divide this by P of P, comma, F, the data. And that's called the evidence. Yeah.
CLR and CFL as an index.
Yes.
Are each individually higher or do they together?
Together they are the priors, but individually they're also priors. You can think of this as the prior on R, and this is the prior over all parameters, all unobserved parameters.
We have to divide by the word of P, L, that is equal to the standard.
So, okay, yeah, let's just do this, sorry. Now we're picking up too much breakdown of that. So this is the same, this is the joint probability, this is the factorized joint. You can also factorize the joint the other way. So that'll be P of L. Actually, this also tells you how to do the inverse factorization, because you just have to read the arrows backwards. So P of L oh, actually, we can't separate that. We have to write it like this. There. That's another way of factorizing it. It's a little bit less nice because we can't actually break up the relationship between all of these things. But then this is the posterior in our case. So we have to divide this whole line by that in order to get this. Let that simmer while we take a break, and when we come back, we're going to be doing this. You're going to be doing this on the board for some other models that we're going to write down, so we can go through it a bit slower. Sorry, we rushed through that. All right, folks. For that kind of stuff. Okay.
So we will take a half-hour break and return at 10:30. A couple of announcements. So make sure to bring your sweatshirt tomorrow. We'll do a group photo. And if you have not turned in your paperwork, make sure to turn that in as soon as you're able to. And if you have any questions about the paperwork, feel free to ask and we'll sort it out. But yeah, usual DSFP rule applies, which is in the break, have to spend at least some amount of time not looking at a screen. And as always, you're welcome to go upstairs, but please be mindful that there are offices people are working in that sort of thing. Have a good break.
I'm very sorry we ate into your break. The screen controls are not, oh, they're there, never mind. Okay, so we're going to start back off with another example to introduce one more component. Yes. Share my screen. Yes. Thank you. Cool. So we're going to start off with an example to introduce one other component of graphical models, and then we're going to do some more problems. So the example that I wanted to do is fitting a sinusoid to data. So it's a little more, the next level from fitting a line to data. So the setup here is, imagine we're given some time series data, and I guess depending on your subfields, you can imagine whatever time series data you want. But I like to think about fluxes in a light group, for example, or a star, maybe from TESS or point is we observe flux as a function of time, and we see some sinusoidal variability. We know the times perfectly well. So the times of the observations that we have, no uncertainty, but the fluxes have Gaussian uncertainty. So we then have some set of time. The flux is f sub n, and then we have some uncertainty sigma n. And the n is just an index to keep track of which flux measurement we're talking about. And the goal with our model is to infer the mean flux, f naught, the period, and these two amplitudes, a and b. So this is a sinusoid, what I would call a sinusoid, which is, you can either write as mean flux plus amplitude times cosine of this plus phase and no sine, or you can do it in terms of an amplitude of the cosine and the sine terms independently, and then get rid of the phase. Everyone happy with that? Okay, so this model, the T's, this is a functional model. I said I would say a word before the word model. This functional model or parametric model has the mean flux, two coefficients, and the period. And the 2 pi and the t are things that we'll know because the t is the input to this function. So the 4 parameters are here. This is how I would write a graphical model for generating the fluxes f given those 4 parameters. So what's going on here? So if you ignore this rectangle, you notice it's a simple model, graphical model, because the data are the fluxes, and all of the parameters just point to that. So there's no relationships like we had before, where we have multiple unobserved things and multiple observed things. Here we just have one observed thing, which is a time series of flux measurements, and all of the model parameters point to the observed flux. Why is there a rectangle? So this is called a plate in the language of graphical models. And this indicates that you have to repeat this, whatever is inside of this plate, this rectangle, some number of times. So in this case, you often, as a convention, you see something like this, and 1 to capital N, to tell you how many variables, or how many pieces of data, in this case, are contained within the plate. Yeah?
Where does sigma n come from?
So these are fixed things, the times of observation and the uncertainty on the flux. And I'm going to assume that we're just handed these things from the test survey or from LSST, Rubin, that we are given flux measurements in some filter, and associated some other columns in our table are the times and the uncertainty of the flux. And these are just given things, fixed values. But they appear inside of the plate because for every flux measurement we have a time and an uncertainty. Is that cool? So now I promised we would be doing some factorizing of joint probability distributions like we started to do before. Notational thing, I don't know if you've seen something like this before. There's different ways of putting in a set of stuff into a probability distribution. So in this case, this is to say that we have capital N measurements of the flux indexed by little n. Sometimes later or tomorrow, I think, I'll turn that into a bold symbol F. That's just like a vector of values. But today we'll stick with this kind of set notation for that. So again, the joint probability distribution, as we talked about just before break, is you have to take everything that's in a circle, not the fixed things, and put it into a probability distribution. So A, B, E, and F naught, those are our unobserved parameters. And then all of the fluxes, so you can imagine this saying F1, F2, F3, etc. That's big, that's a huge structure, so that's why I created it for this. Before I just jump right to how to factorize it, what are some things that we can see from the graphical model already? So what things have no dependencies to other things? What objects have no arrows pointing in to them?
A, B, C, and
Good, the parameters, right. So that right away, when you see a graphical model and you see nodes or vertices where there's nothing pointing in, that tells you that when we factorize, those things are just going to have P of things. So it'll be P of A, P of B, P of P, and P of F naught. And those are going to be the prior probability distributions over those 4 parameters. So however we end up doing the factorization, we'll see that. So then I tend to read down. So next we're going to have P of F sub n. So the probability of all of these flux values, the observed flux values, and that depends on those 4 parameters. So we're going to have some expression that also looks like P of this structure given all of these.
Adrian,
Yes.
it is the same as say that like our prior parameters are independent of others.
Correct. Yes. Good. So there's the joint probability distribution. That's what we inferred from the fact that the model parameters here have nothing pointing in at them, that we're just going to have a bunch of P of. And then there's the huge P of F1, F2, F3, F4, et cetera, which itself would be a big joint distribution, the probability of all of the flux measurements, given the parameters. But oftentimes when we draw this plate notation, we also implicitly mean that the data or the thing that's inside of the plate is conditionally independent. So what does that mean? Right over here. Maybe I can squeeze over here, although I'm not sure that'll appear on the iPad. Right. So really what we have is P of et cetera. Can everyone see that, or is that too hard? Should I put the screen up? Can you see that?
Yeah.
Okay. When we say that things are conditionally independent, that means, so normally if we were to factorize this, we would have P of F1 given F2, F3, et cetera. Conditionally, and then P of F2 given, et cetera. Conditionally independent means I can just factorize this into P of F1, P of F2, P of F3, et cetera. And so that conditional independence condition means I can turn that big joint distribution over the data into a product over each individual evaluation here. So what are the names of the things that appear in here? So what are these called? Prior. And then what would we call that thing? Excellent. Good. Okay. I'm going too slow, I guess. Yes.
Do all of your parameters have to be real?
Real values?
Yeah, could it be complex?
They can be complex. Yeah. Oh yeah, any other questions before we jump into a problem? So this is the new thing. Oh yeah.
So when would it be not conditionally independent? I get the math example, but
You mean when you say when?
yeah.
So one example of a case where things are not conditionally independent is if you were using Gaussian processes, the type of model which you may encounter at some point and may be useful in what you do. The core, one of the foundational elements of Gaussian processes is that the data that you have are not conditionally independent. The generation process, another example is like a random walk, where you have the next value in your sequence depends on the value that you had before. So you wouldn't be able to factorize that into a set of independent things.
So the right-of-ways are conditionally independent, either because the priors are like independent of each other.
No, this is telling us that the data points, individual data points, are independent of one another. But notice this doesn't tell us whether these things are conditionally independent. So it could be we could have arrows actually connecting, like A could produce B and then B could produce this. And then we wouldn't, so then then over here, we would have the joint P of A comma P, and we wouldn't know that just from looking over here. The conditional independence here just talks about the data point. Any other questions? Okay, so now that we've done a more complicated example, we're going to step back and go back to the straight line example, or problem, I guess, that you encountered before. So I can get out of my oh, that's too far. So you may remember, oh, I'm sorry, I meant to do one other thing. So I just wanted to emphasize that now we've added one more component to graphical models, one more like building block. And I think that's it. I don't think we're going to talk about any others. We have unfilled circles. Those are the unobserved parameters or latent variables in a model. There's the filled ones, which are the data, the things that we observe. The edges, the fixed points, the fixed nodes, which are fixed values like pi. And then plates, which tell us about, in this case, the how much we repeat an expression. And in this case, again, it's because the things that are inside here are conditionally independent, so we can expand them into a product. So those are all the important building blocks of a graphical model. And now we're going to put them to work in terms of the straight line. So I looked back at DJ's notebook to make sure I did the same notation, because the number of ways to write this expression are numerous. Y, so the data in this case are going to be Y, measurements of Y. And for each measurement of Y, we're going to have a measurement of X that we know perfectly well. So you can think of this, maybe this flux of this time. This is some quantity where the relative uncertainty is so small that we can just ignore the uncertainty. And so the functional model for predicting the data is closed X plus B. We're going to assume that we measure the data of Y with some Gaussian uncertainty. And so the probability of Y given model parameters is just a normal. Have you seen this squiggly fancy N for normal? Good. Okay. So this is normal of data Y given the predicted Y and the uncertainty. By the way, when I use fancy N for normal, I always put the variance N instead of the standard deviation. So you'll see it's squared. And the reason is just because that's the more fundamental quantity, and it's an easier quantity to work with Gaussian, because if you convolve to Gaussian, the variances that get added, not the standard deviations. And so later on, I don't want to have square roots all over the place. It's easier to work with the variances. But just note that the thing inside it under the squared is the standard deviation, but this is the variance. That's the expression. And then our posterior is going to just be, as you probably saw before, the product over our data points gives that with means given by the predicted model evaluated Y's at the X that we have, with the uncertainty that was again given to us, and then the priors over the slope and the intercept. So given that, we're going to write down graphical models for this using plates, using a plate. So this is another case where we're going to go to the board or work on your notebook. And let's only do about 5 minutes, maybe. So we get I guess I mean, yeah. I really knew two times in general. Okay, good. Yeah. This is a normalized Gaussian, meaning that it equates to Y. So this is the expression. The way we find Y, and then plus some variation. This is just telling you that all the this is not important for the graphical model, but you're going to code up the model and this is just saying that, actually, this is saying that when I evaluate I'm going to evaluate theta y minus and and then product with thank you. Good place and good drawings up. Looks great to me. How does everyone else feel about that? Is that about where you got to? Yeah.
If the x is the same for all y, should it be inside or outside plane?
The x is not the same. So this is a fine way to do it. There's some like design elements of how to actually write the variable names here. But the fact that x appears in the plate means that there are as many x's as y's, and that is the case that we're in, because if you remember, reserve points like this, and so each of these points is an x1, y1, and this error bar is the sigma 1. Cool. Yeah. So right, if you wanted to get fancy, you could go that. It's like n here. But that's totally fine. Everyone feels good about that? All right. Cool. So now the next problem we're going to do is a bit more complex, and it's going to put together everything we've gone over so far. But before we go to that, I just wanted to take one moment to introduce something that I find useful. This is kind of like going back to previous days, thinking about probability distributions and working with probability distributions. Something that I think is useful, which you may not have come across yet. And so we're all astronomers or astrophysicists, right? Or are there people who have not taken physics and thought about units? Yes, that's the question. I personally find it useful to think in terms of units, because a lot of expressions, that's like a good way of debugging math, and especially in code. If you put the units into your code and you end with a variable and you try to convert it to parsecs or flux units or something like that, and it doesn't work, then that tells you have an error somewhere. Similarly, you can actually think about probability distributions in terms of units, and you can debug them by making sure that the expressions you have the right units. So let me explain what I mean by that. It's going to be right. Actually, it's so pretty, I'll leave it up. So, that's right bigger. So you saw that probability distributions have to integrate to one like this, right? Now, what units does x have? Whatever units x has. X is a variable. So this could be something like, distance or time or flux, whatever. X or dx is going to have units of whatever x, the quantity x has. So what does that imply about P of x?
Inverse x.
Exactly. So P of x has units of 1 over x. So that sounds like a simple or maybe an obvious thing, but when you start to have very big probability distributions, expressions like that, one of the first things I always do is just check to make sure that the units work out. When I integrate the thing over the parameters or over all of the quantities that I have, it has to come out dimensionless. And so that tells you a couple things. So one thing is that what do you do about conditionals?
What do you think?
So
Whatever actually whatever experience
good, yes. Yeah, so this thing does not have units of beta involved in it at all. So anything to the left of the conditional, the distribution has units of 1 over that. If we had something like K, we can integrate this over all of those things. That should come out to 1. So the expression that I put inside of this probability distribution has to come out with units of 1 over x, 1 over y, 1 over z, 1 over k, multiplied to 1 another. So keep this in mind. I think it's a good way of again, it's a tool for like debugging and assessing models and big complex probability statements that you might write down. But remember the rule that if we had a conditional here, this is the thing that integrates to 1. And the only way we could integrate out all variables would be to have things that have units of 1 over those variables. So now, this would be a valid way of getting to a dimensional quantity. Cool. That was a brief tangent. Back to here. Okay, so now we're going to move on to a bigger problem, and we're going to take a bit more time to do this. And this is a fairly advanced thing that's going to involve all of the tools that we've learned about already. So if you get stuck, that's totally fine. Just raise your hand, and we can chat about whatever you're stuck on. But the problem is the following. We are given an Eshel spectrum. Raise your hand if you've heard of or worked with Eshel spectra before. A couple people, so you can help everyone else. But in simple terms, an Eshel spectrum is like a spectrum, flux versus wavelength, that's been chunked up into a bunch of distinct sections and then dispersed over the vertical direction as well. So it's kind of like a two-dimensional, you can think of it kind of like a two-dimensional spectrum, or as a spectrum that's been cut up into a bunch of sections. So each section is just a block of wavelength, in my simplistic understanding, flux, wavelength, maybe emission line, absorption line. So an Eshel spectrum is like taking this part and calling this chunk 1, this part chunk 2, and then maybe whatever's over here, chunk 3, like that. So we have flux, measurements of flux. We have the values of wavelength that correspond to the flux, but we also have some grouping of the flux measurements now into these chunks that I'm calling. I probably call them something. This is an example of a two-dimensional Eshel, sort of Eshel spectrum of the sun, which you may have seen before. So each row here is some block of wavelength, and then this is the next block of wavelength, etc. So there's a lot of words here that I'm not going to say out loud about the exact notation to follow here. But the idea, yes, so that what I'm calling chunks are actually called spectral orders. We're going to have some index that corresponds to spectral order, or whatever chunk that you're in. And then we're going to have a separate index, which relates to where you are in wavelength, like what pixel value you're at. So now we have 2 indices floating around now. which might tell you hint we might have 2 plates in the graphical model that we're going to write. And the ultimate goal here is we want to take the spectrum, the flux as a function of wavelength, and our model we would like to infer is the radial velocity of the star. So that's a single one. So pair up with your partner, read the notation stuff, start thinking about it. If you get stuck, raise your hand. We can also bring things up to discuss them while we're going through it. But same task as before, we want to draw a graphical model for this more complex example. Good. This graphical model. So let's look at one example, and then we can talk about the different aspects of that. Let's see. Let me look at the words for a second. Actually, a lot of them are looking pretty good. So good job. Does anyone want to volunteer to try writing one up here and talking us through the structure that you come up with? Do it. All right.
So we like erased and thank you. Let's just erase. Okay. We like erased and changed it like 5 times.
That's good. That's the
So the first thing we did actually was we said there's multiple orders and then there's going to be lines within each order. So we figured the boxes would be nested. Where that's the various lines, they're M for each order K. We started kind of like with our goal, which is going to be these RV measurements. And that's going to require a measuring, like it's going to be a lambda not the same like a reference wavelength, and the RV is going to come from this difference, where that's the mu. I didn't know how to say like lambda, like mu measured lambda or whatever. So there's going to, measuring the RV, there's going to be some reference wavelength. And we're going to measure all of these lines. So that was mu m. And that'll go in this direction. For all of these, we'll also measure a sigma. Something like that. Or we'll estimate a sigma. But these ultimately come from measuring the flux at each spectral order. So this is going to be the measured stuff, the actual measured stuff. They give us 2 circles or a shape. And then that we said came from an A K and a B K. We first thought those were dots because that might be like a set thing by the spectrograph, but that doesn't make sense. So that's probably just we measure that continuum. It's like fit for it somehow, like that y equals mx plus b. And the last thing that we need to know the location, like the actual wavelength of the line, we might know like the pixel, but we won't know where it is that set of reference wavelength. We figured those are going to be known, and then that'll feed in something like that. That was it. Yeah.
Good. Love it so far. Does anyone have comments or questions about the? Yeah.
Yeah, I just have a few comments.
Good.
First, I think it is mentioned that there are M spectral features in the overall spectrum, not in just in each chunk. So maybe this is not a nested structure. The plate of the M absorption feature should be outside the larger plate. I mean, the orders, the different chunks.
Good. Yeah, that was a confusing thing in the way that I was trying to come up with an example that had this kind of structure, and so it's a little convoluted because that's not necessarily how you might use it in practice. But the way that I specified it is that the M's are over the full spectrum, the full F over all spectral orders over all chunks, whereas the K's are per chunk. So exactly as Chang said, what you could have done is actually pulled this plate outside of, it doesn't have to be nested inside, there could be two plates next to each other. That's a valid way of doing a graphical model.
The reason we did it this way was because we said this is an implied sum over M and over K, like two sums, and like there would be all of these M's within all of the chunks. Like you have the whole spectrum, but in order to make the whole spectrum, you have to first look at each chunk. Is that not the right way to interpret these nested boxes?
So that would be right if I said each chunk has M sub K lines.
Yeah, okay.
But because I said the full spectrum has M lines, then it doesn't have to be nested.
With that little K, then?
Yes.
This is all right.
Almost. Actually, let's see. Since that was a great comment. Let's see. Tony.
Yeah, we succeeded. Yeah, we flipped our cards.
Oh, okay, good. That really. I don't know anyone, so that's sorry. Good.
Oh yeah, I forgot that. Thank you.
Good. Okay. Let's talk about the direction of that arrow. Okay, that's good. I like that. Again, with the comment that we can pull this inner plate out. Mariam? Thoughts?
Yeah, you're right. I think that's okay.
Awesome. So you can move that arrow.
Right, so that's also something we measure from the quadratic concept.
Good, like that. In fact, why don't we just do the extrusion? And put this other plate here. Let's start there. That's Marcus trying that marker. Yes. Here, switch to this one. We get everyone to death.
Exaggerating that a little.
Okay. Cool. So now you can redo. Yeah, let's just, well, we can truncate that. Take that smaller. You could have moved it closer, but that's fine.
And then this fed into, I guess this would feed into both of these.
Does it?
No, I was right.
Thoughts from out there on that arrow? Right.
That'll be left.
That actually is the F.
Oh. So I calibrate it from there and then get those two out of it?
Right. I guess, yeah, one way to see, it doesn't necessarily have to, but you can think of these could be maybe in pixel space, and that's what gives you the connection to wavelength or something.
So could you explain a little bit, what is the difference of lambda naught and lambda k?
Lambda, not isector like the ultimate RV measurement. You're going to have, like RV, you need a difference between two wavelengths.
Yes.
This is going to give you the wavelength that you actually observe. But that still doesn't mean anything unless you know how far from the line
So
that should be there.
then what is the difference? Mu m and lambda k.
Mu m, lambda.
Mu is
Yeah, right.
That's right.
U is the observed wavelength or over spectrum.
That's lambda. This is the observed.
The sentinel perspective.
this is the unknown. This is an unknown latent. This is the line centroid for the M spectral line.
Yeah, so that's you in the center of the spectrum you're fishing for. That's unknown, yeah.
Exactly, that's an unknown. Yeah. So good. So I think that this calls into a good question. Somewhere we have reference values of where each spectral line should be.
Yeah.
But it's not one value out here, right? It's actually
M value to be
exactly each line has a known laboratory measured value. So actually you'd have a lambda naught inside here, and lambda naught comma M or something.
and that contributes to UM.
Exactly. That doesn't. That the only connection to the RV is that the RV with the lambda is the predicted location of mu. So this line can turn into a line that way. Right. Cool.
Oh, mu is the RV.
Mu. So okay, let's do it over here. So this is some. Actually, let's do it. Thank you for being brave.
No.
Okay, does that help a little bit? So let's get rid of that line, and then I think I'm testing this. Cool. That looks pretty good to me. So the radial velocity here only enters our model through shifting the laboratory measured values of the lines to the observed, but the unobserved, but model parameter centers of all the spectral lines. And all we get from the spectrograph is flux in these spectral orders, which have some straight line continuum flux behind them as well. So within each K spectral order or chunk, we have a straight line background. We have some number of lines, which is maybe 1 or 2 or 10 or whatever. But over the whole spectrum, we have M total lines indexed by the little m. So I think I'm happy. Yeah.
Each spectral order does not have same length. Right?
We didn't specify really. Yeah.
And then is there sigma M and RQ?
Sigma M. And RV, no. Yeah. This is inside baseball for the domain application, but for example, we could have V sin I. That's something that would, that's the rotation related to the projected rotation of the star, which broadens the line, so that would draw into the widths of the line, sigma M. Yes.
Clarification, what is, so the double circle around FOK, that's just a box, right? So
this is just shaded, because that's data.
but are you putting box around that? Because that's within each chunk is a function. Are we doing that?
So this is okay. Another thing we could have done is actually put the full F outside, and then had everything point to that. Have the two plates point to the full array of fluxes F. That's another thing we could have done. But yeah, because one limitation of graphical models is that this is an okay way of structuring it, but this hides an independence that's there, which is that not all of the mu's and mu m's and sigma m's generate the f's in a given order, because only some of the lines will be in that order. So that's just like, there's no way of really drawing that clearly here. We'd have to restructure everything and add some other notation. So another way of doing it would be to just put the F out, like further hide that and put the full array of fluxes out here, have everything point to that. Yes.
So for each M, like the whole chunk, like it would run K from 1 to capital K, right? Or like for each M, for each K.
What do you mean by that?
Like for example, if n equal to 1,
Yep.
so K will run from 1 to M, like whole chunk, or like if only K equal to 1 for M equal to 1.
There's no interaction between the M and the K in the way that I specified the problem, which is why I was saying, so here, let me show you how I originally envisioned the solution, which again is not the, I didn't put it in here. Not the only way of doing it because of that degeneracy, notational degeneracy. So this would be, oh, and I forgot to put the velocity. There should be a velocity pointing in here. But you can also separate them and have everything point to just, I have the full array of fluxes. Sorry, there's an error. Velocity.
My question is like, how then like A and M, we can choose the values of A?
Oh, well, that just depends on like, okay, right. You're asking a model building question. That goes too much into the weeds of like,
Which one would you start for, like M or A?
It depends on the data that you have, I think. I mean, like you're given a spectrum which is cut into some number of spectral orders. So that'll set big K. And then you have to pick your however many spectral lines you want to fit. It depends on the data that you have. There is no
relation like A and M.
No.
Like,
Yeah.
There's one thing I'm not quite sure on. So before that, we had like y as a function of x.
Yes.
Y wasn't there in it. So we put it in a ball.
Yeah.
Or it doesn't matter.
So I defined F lowercase symbol like that to be the full array of fluxes, which has
Okay.
you know, it's like an array of SKs.
Yes, but even
So you could put like we saw in the example that's on the board, you could put F sub K in this box.
even in the board, each f sub k is a function, is an array.
Correct.
Do we not put boxes for that, for the fact that it's an array?
Oh, I see what you're saying. Yes, you could also go further down and do a box like within each K order, there are n pixels. You could do that.
But it doesn't matter.
It kind of, the way you draw the graphical model, there's design aspects to it in terms of what you want to convey and how deep you want to go into the specification of the model. So that would be totally valid to expand the pixel dimension as well and have another box for pixels. Yeah.
Yeah, could you just maybe show like real life example from paper or something?
Of a graphical model. I'm not gonna pull. Well, okay, I thought I had examples at the bottom, but now I don't see them. Why don't I compile a list of a couple in different domain applications? I thought I had done that, but I'll send them around. Okay. Back to here. So I guess the point of this more complex example is to reveal that with all of the building blocks that we have, there are decisions that you have to make about how much detail you want to give about a model and at what level you're trying to pitch it. So there's kind of, if you were going to put it in a paper, you have to think about like what's your audience for looking at the model. And if the audience is you, maybe you want to put every aspect of your detail of your model into it. But if your audience is like someone that you just want to convey the general structure of the model to, then maybe you would not do the pixel sum, for example, in the case, or make other decisions about what to leave out. Good. Deep breath. Good job, everyone. In the last 5 minutes, I just want to flash a very quick preview of what we're going to be talking about tomorrow, because all of these components are very useful for thinking about the topic of hierarchical models. So let's look at a quick example and talk about how it differs from the types of models that we've been looking at so far. And so we're going to return to this, which is a more verbose version of the same model that we started with. We have a measured parallax. We want to lend the distance. But now notice I put a couple more fixed things on just to remind us. So we have a prior on the distance, and that we're going to assume that that's a Gaussian. So that has a mean and a standard deviation. And in the case of the model that we talked about earlier, those would just be fixed values that we plug in as numbers into the prior over distance. We also have for each observed parallax and uncertainty. That all cool? Now, what if we measure parallaxes for 10 stars, or Gaia gives us the parallaxes for 10 stars, and we want to actually learn or infer the mean value of the distance, not the parallax, the mean value of the distance for that set of stars. So in order to do that, we need a plate. We have some conditional independence. We have independent measurements of parallax for a bunch of stars. Those are these. But now each star, in order to get to learning the parameters that we care about, which have gone from being fixed values to things, unobserved things we want to infer, we now have this unobserved latent variable, the distance to each star, for every object in our sample. So notice that now for each object inside of the plate, we get a parameter r. So you could write this as r sub n, parallax sub n if we wanted to. And those unobserved latent variables then connect up to the things that we want to infer, which are the mean distance and the variance, the standard deviation of the distance along the line of sight. So this is now a hierarchical model. And the reason it's hierarchical is, or another word for that is multi-level, is because we now have multiple levels of, above the data, we have multiple levels of random variables that are stochastically related to one another. So R can be directly converted to a parallax and then put into a likelihood, like a Gaussian, where we have Gaussian uncertainty. But now we're saying R itself is drawn from a distribution that has parameters that we don't know, the mean and the variance. So that makes this multi-level instead of before we just had one-level model. And that is my preview for tomorrow. We're going to talk about that concept in a lot more detail.